Welcome back to our session. We're still talking, working with redox reactions. So we now have identified the fact that we are able to, look at a redox reaction, from different perspectives, using practical examples of reactions that involve metal and acids. Or you can think of the same reaction in terms of the transfer of electrons. Now we'll try and look at more examples of that and see how exactly we can, try and identify the role of different species, in terms of your oxidizing agent as well as your reducing agent. Right, so now we want to also compare the reduction potential in terms of the two substances involved, one being able to readily donate, the other one being able to actually readily accept electrons in terms of the standard reduction potential. So this is some kind of a reactivity series of some sort. Now let's look into that. Okay, now we understand that displacement reactions have to do with the comparative strength between, two substances. Say, for argument's sake here, we're comparing, magnesium and zinc, in the context of a reaction between a metal, okay, and a salt in this case, right? So these are displacement reactions. So our comparison is confined to magnesium and zinc. So we are saying that magnesium has displaced zinc from the solution. The solution that we're talking about in this case is zinc chloride. Now, why are we saying magnesium has displaced zinc? You'll see that in the solution now we have got magnesium chloride instead of zinc chloride. And then zinc actually is produced as atoms. At the end of the day, we can say that magnesium was able to displace the zinc. Right. So, or if you can think of displacement in terms of substitution, where there was zinc, now there is magnesium. That's what we exactly mean when it comes to the displacement. Right. So the half reaction, which actually shows the reduction, is that zinc ions in solution are reduced. The process is reduction. So these zinc ions in the solution are actually our, zinc ions are our oxidizing agent, okay? So this oxidizing agent is actually the substance or the species, the ions that undergo reduction. All right, okay, and then let's look at this one. In this case, we've got copper chloride solution, all right? So say for argument's sake, we've got a solution of what? Of copper chloride, okay? Right, so in this copper chloride, which ions are present in this solution? We've got the copper ions, all right, as well as the chloride ions. Very, very important. And then if we put some zinc metal into this, a reaction will take place, okay? But essentially, what is happening here, zinc has displaced the copper, all right? That's why at the end of the day, in solution, we now have zinc chloride. So what role does zinc play in this reaction? Now we understand that zinc atoms undergo oxidation to give us Zn2 plus 2 electrons. Now zinc being the substance that undergoes oxidation, then zinc becomes our reducing agent, okay? So zinc is more willing to it's zinc, because zinc undergoes oxidation, it is more willing to lose than copper. That's why zinc is able to displace copper in solution. So it is a reducing agent, right? And then now we are saying that zinc is the reducing agent because it undergoes oxidation, okay? So this is the process. So in a nutshell, we are saying that zinc is more willing to lose electrons compared to copper. Hence, it can be explained by this half reaction that we see below, right? And then also, we are asking ourselves, okay, what if we compare zinc in these two reactions? Now, we can do so by way of tracking the changes in the oxidation numbers. So in reaction 1, zinc undergoes, because here the oxidation number is 2+, zinc undergoes actually, let us put it this way, okay? This is what we are saying, okay? Zinc ions are actually reduced to give us zinc metal. So this is plus 2 electrons. This is for reaction 1, all right, Zn, right? But in the second equation, zinc undergoes oxidation. So it means Zn, okay, to give us zinc ions in solution plus 2 electrons. Now we're looking at the same substance in 2 different reactions. Now the question is, what happens to zinc in the 2 reactions? By now, what is it that we know? We know that a substance that shows a greater willingness or readiness to lose electrons is actually a stronger reducing agent, okay? So on the same note, we are saying that if a substance is a stronger reducing agent, you can think of it as being a weaker oxidizing agent. We are saying the same thing depending on how you look at it. But if you look at it in terms of losing electrons, it's a stronger reducing agent. In terms of gaining electrons, it's a weaker oxidizing agent. But in 2 reactions, the same substance undergoes 2 different reactions, right? So the spectator ions in this case, if you come to think of it, if you look at chlorine on the left here, it's -1, -1. So chlorine is not involved in the transfer of electrons. That's why I would refer to it as a spectator ion, right? So in reaction 1, zinc is actually undergoing a reduction, which is the gain of electrons, right? Now, if we look at it in the second reaction, zinc undergoes oxidation. So in summary, 2 things may happen to zinc. The double arrow there shows us that there is a possibility for zinc ions to be reduced or for zinc atoms to be oxidized. So you may choose to read this equation from left to right or right to left, depending on the reaction in which zinc is actually involved. So remember the analogy of the 6 and 9. We're still saying the same thing. It entirely depends in terms of with which substance are we comparing zinc. So the double arrow suggests that there are 2 possibilities here. If we read this equation from left to right, we can have zinc 2 plus 2 electrons to give us zinc, okay? Or from right to left, we can show zinc undergoing oxidation, okay? Plus 2 electrons, right? So that's the main idea, okay? So that's what it means. So if you compare the strength of reducing agent, displacement reaction, they actually provide a method for establishing a list of metals in the order or a sequence from the strongest to the weakest reducing agent. So a stronger reducing agent will actually show greater willingness or readiness to lose electrons, okay? Now this list, we call it the reactivity series, which is not entirely new to us. So we can write half reactions as reversible reactions, okay, which explains the double arrow that we saw as was the example with zinc in those 2 different reactions, right? Okay, now we are also saying that magnesium is able to displace zinc, and zinc is able to displace copper. So if we are to put this in a sequence or in that reactivity series, so the element at the top, the substance at the top, shows greater willingness to actually displace another one. So we can think of it in terms of that trend or that sequence, right? And then we ask ourselves, where does silver belong in the reactivity series? So if we go back here, okay, you realize that magnesium can displace zinc, zinc can displace copper. Now, according to this reaction, copper can displace silver, okay, because now we have got zinc ions in solution. Now, we ask ourselves, where does silver belong? We are able to locate silver as per this equation to say because silver can actually be displaced by copper. We can then arrive at the thinking that copper is actually above silver in terms of the reactivity series, meaning that copper, zinc, actually magnesium is the strongest reducing agent of them all. As a result, we are able to come up with this series, whether you look at it from top to bottom or bottom to top, Right. So these are some of the ideas that we actually need to try and understand. So if we think of, different elements, we can think of hydrogen, in terms of the reactivity series. But then these are some of the, the thinking in terms of comparison of the reactivity series, which is something that I would also want to look at after our short break, and then we'll try and discuss more examples and look at the standard reduction potential tables. For now, let's take a short breather.